So this first question, we've got two curves here. So we've got C1 is this top curve here, so it's in red on the board, and C2 is this bottom curve here, which is in blue. We're just looking between 0 and pi over 2, so just in the first quadrant here. And it wants us to find the area enclosed by C1, C2, and the half lines theta equals 0 and theta equals pi. So that's asking for this area in here. If it had just said between the curves and the initial line on the half line theta equals 0, it would be this area on the right here, because it included pi over 2 once this one is. Yeah. So first thing that we need to do is find where these curves cross. Okay. Just like you would for normal integration, find the point of intersection. That will help us with our limits of integration. Okay. But we will need to think a little bit more carefully about what areas we're going to work out in this case. It's not just a case of subtracting them and things like that. So let's find the point of intersection by setting these curves equal to each other. They're both r equals. So we've got 2 minus root 2 plus theta equals root 2. Plus theta. Get the cos theta on the same side, so add that root 2 cos theta across, so you get 2 root 2 cos theta equals 2. If you divide 2 by that, you get cos theta equals 1 over root 2 or root 2 over 2. And it gives you one solution between 0 and pi over 2, which is theta is pi over 2. We don't need the r value really, the theta value is the important bit. Now let me get rid of it. So you've got to think carefully about what polar integration kind of means, and think carefully about what's happening with these curves. So let's think about the red one first. So let's think about C1. So when theta equals 0, we're starting out here. And then as theta increases, we're going up this curve until we get to pi over 4. So if we integrate between 0 and pi over 4, if I draw the half line in up to pi over 4, I'm going to find this area in here. Okay, that makes sense. So increasing my theta as I go around until I get to theta equals pi over 4, and that's the area that I'm finding if I was to integrate C1 between 0 and pi over 4. Obviously, to work out the whole area, I also need this little bit in here. So I need to think about what limits of integration that's going to be. And it's a little bit less obvious because there's it looks like there's 2 places where C2 is on the initial line. So if I think about when theta equals 0 for C2, so theta equals 0, cos theta is 1. So this is at root 2. So this one here, this point here is theta equals 0. Okay. So if I was to do the integral between 0 and pi over 4 for C2, we're starting out at theta equals 0 and tracking all the way along up here, I'd be finding this entire integral in here, which isn't what I want. Okay, so I'm not using between 0 and pi over 4 for my integral for C2. Instead, I'm going to start at pi over 4 and then go this way all the way down to here, which is at pi over 2 for the blue curve. Okay, so I need to work out those 2 areas and add them up this time. So you've got to think really carefully about these polar integrals. It's not just a case of integrating them between the same limits and subtracting them like it is for normal integration. You've got to think carefully about which way around your curves are going and what limits you're doing and stuff. It's not necessarily the same. Okay, so I'm going to work out those 2 areas there and add those up. And so there's a lot more space over here. So we've said we're going to find first the area enclosed by C1 and the half lines theta equals 0 and theta equals pi over 4. Okay. Remember area, I call that A1. So area for polar integration is a half r squared d theta. For the red one, we're doing 0 to pi over 4. The equation of C1 is that 2 minus root 2 cos theta. Half times the integral of 2 minus root 2 cos theta squared between 0 and pi over 4. And now it's a case of expanding that out and integrating cos squared and all that kind of stuff. So expanding this out, I get 4 minus 4 root 2 cos theta plus 2 cos squared theta. Not a lot of spaces. So then I'm going to use my double angle formula for cos. I'm going to use that cos 2 theta is 2 cos squared theta minus 1. Because I've got 2 cos squared theta here, I can just swap it for cos 2 theta plus 1. This is half the integral pi over 4 is 0. 4 minus 4 root 2 cos theta. And that's cos 2 theta plus 1. Obviously, the 4 and the 1 you can combine to give 5. Let's do this integration. You can take the half inside if you want, or you can leave it outside. It don't matter. I'm going to leave it outside. So 4 plus 1 is 5. Integrating 5 with respect to theta gives me 5 theta. 4 root 2 cos theta. Cos integrates to sine, so that's minus 4 root 2 sine theta. And cos 2 theta integrates to sine 2 theta, and it's divided by 2. Between pi over 4 and 0. Substitute your limits in. So I've got 5 times pi over 4 minus 4 root 2 sine pi over 4 plus a half sine pi over 2 if I sub pi over 4 into that 2 theta. And if I sub 0 in, I do get 0. So obviously theta is 0, sine 0 is 0, sine 2 0, 0. So I've got 5 over 4 pi times a half, which gives me 5 pi over 8. Sine pi over 4 is 1 over root 2, root 2 over 2. I've got a root 2 over here, so it's going to cancel with that, and I'm just going to get minus 4 for this kind of middle term. Times it by the half gives me minus 2. And I've got sine pi over 2, which is 1, times a half, times that other half, so plus a quarter. My exact area is 5/8 pi minus 7 over 4. You can work out each bit individually in your calculator. Like, don't put it all in at once because it won't give you an exact value. Each bit. We're going to do the same thing for C2, but remember it's not the same limits this time. So for C2, we're doing it between pi over 4 and pi over 2. So area 2 is a half times the integral of r squared d theta between pi over 4 and pi over 2. More straightforward this time. The equation for C2 was just root 2 cos theta. Squaring that gives you 2 cos squared theta. And again, using your double angle formula identity, the cos 2 theta is 2 cos squared theta minus 1. You can just substitute in that 2 cos squared theta is cos 2 theta minus 1. Plus 1 theta. Integrating this again, it's cos integrates to sine, and you divide by the 2. 1 integrates to theta. And you've got your limits pi over 2 and pi over 4 this time. Got a half sine pi if you sub pi over 2 in. plus pi over 2, and then minus a half sine pi over 2 plus pi over 4 if you sub pi over 4 in. Sine pi is 0. So, and we've times all these by a half. So I get a half times pi over 2, so that's pi over 4. Sine pi over 2 is 1. That's minus a half times another half, and gives me minus a quarter. And here I've got minus pi over 4 times by that half, gives me minus pi over 8. So I get pi over 8 minus a quarter for that area. Final step is to add some of these areas up. So looking at the diagram that we had 2 areas that were adding together. I'm not subtracting one from the other one. So the total area is going to be my A1 plus my A2. A1, we got 5 over 8 pi minus 7 over 4. A2, we got pi over 8 minus a quarter. Adding these up, that's 6 over 8, so 3/4 pi and minus 2. For reasonably high function. Unfortunately, I don't think your calculator does area of the polar curves. Would be really cool.
How you found the limit?
Yeah. The limits is the trickiest part about this. Once you've got the limits, the integration itself is not too bad. So you're okay with the idea that integration of polar isn't finding the area between your curve and the x-axis anymore. It's finding like sectors as you go around to theta. So it's this area in here that we want in total. Okay. The C1, we start out here, and as you increase theta, you go up here to theta is pi over 4. The half line for pi over 4 is in here. So you're kind of doing a load of little sectors up to here until you get to pi over 4. But this is the area that we found. This is A1. Now for C2, I need to know which way around C2 goes. I need to know, does it start here and go around to the left, or does it start here and go around to the right? Because if it started here and went around to the right, it would be fine. It would be between here and but it doesn't. It starts over here, because if you sub theta equals 0 into here, you get √2. It starts over here. And as you increase theta onto pi over 4, you get up there. So if you were to integrate between 0 and pi over 4, you would find this area in here. And if we were working out this area, you would take them away. But we're not. We're working out this area. So instead, I keep going around here until I get to pi over 2, it's back down here. So like your half line starts pi over 4, and you do a load of little sectors going around here, so you integrate in between pi over 4 and pi over 2. Told you that's the hardest part.
Thanks, great.
Okay. Any other questions about what I've done here? I think once you've got the limits, really, it's not too bad, but getting the limits is tricky, isn't it? Right, let's have a look at example 2. So again, we've got 2 polar curves here. We've got C1 is r equals 2. So that's just a circle centered on the pole with radius 2. And we've got this curve here, so 1.5 plus sine 3 theta, which is this curve shown in the diagram. And both these just between 0 and pi over 2. To find this area again, first thing we want is where these curves intersect. So there are 2 here, which we should be finding, this one and this one. So let's do what we normally do, set these equal to each other and solve it, which isn't too bad to do, really. So you've just got 1.5 plus sine 3 theta is 2, minus the 1.5, 5, inverse sine this, 3 theta is pi over 6. And we can get extra solutions for this. So if theta is between 0 and pi over 2, 3 theta is between 0 and 3 pi over 2. So extra solutions for sine come from doing pi minus that. So I can also have 5 pi over 6 will be included in there. And you know there should be 2 from the diagram. Divide this through by 3, you get theta is pi over 18 for the first one and 5 pi over 18. Second. You could work out R, which we will do in this case because it specifically says find the coordinates. Did it say that before? Just at the point of intersection. I didn't. This one specifically asks for coordinates, so we will find R for these. So when theta equals pi over 8, well, I don't need to find R. I don't need to sub that in. I know R is 2 from the first one, actually. So my coordinates are, my first one is at 2 pi over 18. My second one is at 2. 5 pi over 8. Okay, but the R is not really relevant. But this is the thetas that are in. Okay, it then says the region between the curves which R is bigger than 2. So it's where this second curve is outside the first curve. And for which R is less than a fifth. Sorry, 1.5 sine 3 theta. So that's the inside of this curve, basically, is shown shaded. Find the area of the shaded region, and it tells what format answer should be. So again, we're going to think carefully about these limits and about whether we're adding areas or subtracting areas or whatever this time. So this one here is at pi over 18. This one here is at 5 pi over 8. So let's think about the outside curve first. Let's think about C2. Okay. So if I want to start at pi over 18 down here. So I'm going to draw a half line up to pi over 18. If I was to integrate this between pi over 18 and 5 pi over 18, what I would find is as I go around here, I would include this entire area in here. So I'd include all of this area. That's if I integrate C2 between pi over 18 and 5 pi over 18. Okay, so as I'm going around doing a load of little sectors and adding all of those up like that. For R equals 2, if I integrate between pi over 18 and minus pi over 18, as I'm going around here, I will be working out this area in green. So this time I am going to use the same limits, and I'm just going to take them away from each other. It's worth, well, we don't really need to check, but it may be worth checking, you know, am I actually going this way around the sine curve? But I am. If you put 0 in, you'll start at 1.5 and then you'll increase up until here and go down. So I am this time using the same limits, and this time I am going to just subtract. Okay. So let's do the big area first. So this is a half times the integral of r squared d theta. This is for C2 between pi over 18, 5 pi over 18. For C2, so that's 1.5 plus sine 3 theta. Go ahead, theta. Then I'm going to expand this. I'm going to use double angle formula. Half into 5 pi over 18. Over 18. Expanding this out gives me so 9 over 4, 2.25 for expanding that one, plus 3 sine 3 theta plus sine squared 3 theta. Use a double angle formula for cos again. This time the one involving sine squared, which is that cos q theta is minus 2 sine squared theta. If I rearrange this to make sine squared the subject, I get half minus a half cos theta. And when I put this back in, instead of theta, I've got 3 theta in here. So this is going to give me cos 6 theta. Let's go. And half times the integral between 5 pi over 18. 5 over 18 of 9 over 4 plus 3 sine 3 theta. And then I'm putting in a half cos 6 theta. Sorry, half minus a half cos 6 theta. Let's tidy this up a little bit before we integrate it. So give me 11 over 4. Take the half out of them.
Issues. So yeah, this other stuff. Side of these.
Right. Now we can do the integration. So integrating 11 over 4 goes to 11 over 4 theta. Integrating sine goes to minus cos. So minus cos 3 theta, and I've got 3 at the front. I'm dividing through by 3 because it's 3 theta, so they cancel out. Minus cos 3. Integrating cos goes to sine. I need to divide by the 6, so 1 over 12 sine 6 theta. Between those limits. Sub these limits in. 11 over 4 times 5 pi over 18. Cos of 3 times that, so that's 5 pi over 6. Minus 1 over 12 sine 6 times that, so that's sine 5 pi over 3. And then minus what you get when you sub in pi over 18. This is a long one. Over 18 minus cos pi over 6 minus 12 sine pi over 3. I wouldn't type all of this into your calculator at once. I'd work out each of the individual bits. So first bit, I've got a half times 11 over 4 times 5 pi over 18. That gives me 55 over 144 pi. Cos of 5 pi over 6 minus root 3 over 2 times by that half gives me minus root 3 over 4. Sine of 5 pi over 3. Another minus root 3 over 2. That's times by 1 over minus 1 over 12. That should be positive root 3 over 4, shouldn't it? Because I got minus root 3 over 2 for that cos, and it's minus that, so it'll be positive. So I'm times in again that minus root 3 over 2 by minus 1 over 12 and times it by a half again. So I'm going to get plus root 3 over 48. That one. 2 times 12 times another 2. This one here. So I'm doing a half times 11 over 4 times pi over 18. So that's minus 11 pi over 144. Too many minus signs happening here. Maybe we could expand it. Cos of pi over 6. Root 3 over 2. I've got minus, which again is going to make that positive, and times it by a half gives me plus root 3 over 4. And the last one I've got sine pi over 3, which is going to give me another root 3 over 2. times by a half, times by this other half. I've got minus minus, which makes plus. So that's plus root 3 over 8. You could type more into your calculator than I have done. Which one? No, it's 12, not a 2, isn't it? Yeah, that should be a 12. So that's it's another 48, isn't it? Thank you. Right, so we've got a collector par pies. So we've got 55 minus 11, so we've got 44 over 144, which should simplify to 11 over 36 pi. We can collect up our root 3s. So I've got a quarter plus 1 over 48. And I've got 2 of them. Times 2. Gives me 13 over 24. Yeah, so the green area that we're going to take away, we can do it by integration, but it's an area of a sector, so you can do it by using the area of sector formula as well. So the angle between us, take those away from each other. So take pi over 18 away from 5 pi over 18, 4 pi over 18, 2 pi over 9. So we're going to just use the area of a sector formula, which is a half r squared theta. R is 2. Theta we've just said is 2 pi over 9. Just take those away from each other. So I'll get 4 pi over 9 for that area. So much less. You can do it by integration. It will let me do it. Take these areas away from each other for the total area. 11 over 36 plus 13 over 24 root 3 minus 4 pi over 9. I think I'll get minus 36 plus 13 over 24. That's 2 pages. So we've got a cardioid. So it's equation 4a 1 plus cos theta. And we've got a vertical line here. So that's got equation r equals 3a sec theta. It says the line cuts at points P and Q, and it says prove that PQ equals 6 root 3 a. So we're going to find the points of intersection of these two curves here. So, as usual, let's set these equal to each other. We've got 4a 1 plus cos theta. 3a theta. First off, I can cancel a off both sides because it's just a constant. And I'm going to expand out the left-hand side and write sec as 1 over cos. 1 cos theta. It's 3 over cos. I'm going to times up by the cos and bring everything across to one side, and I'll get a disguised quadratic in cos. So times up by cos, I get 4 cos squared theta plus 4 cos theta. If I minus that 3 across, that's equal to 0. Yeah. Solve this quadratic in your calculator. 3. We'll get 2 values of cos. We get a half and minus 1.5. Cos theta equals minus 0.2 has no solutions because it's less than minus 1, sorry. There's no solutions as cos theta is between 1 and minus 1. However, we get solutions from this one, so I get that theta equals pi over 3. And we're going between, for theta between 0 and, sorry, theta between pi and minus pi. So I also get minus pi over 3. It's because it's symmetrical. We need to find the r value. because it asks us to prove this, so you need to find how far away this is. So you can stick it into either of these. Let's just stick it into the first one. So r equals 4a1 plus cos theta. I'll work this out, and theta equals pi over 3. So cos pi over 3. But we've got that as half. So it's 4a. 1 plus a half, so that's 3 minus 2. We've done something wrong. No, that's fine. And if I get theta equals minus pi over 3, I'll get the same thing. So if you stick in theta minus pi over 3 into cos, you also get a half, so you also get 6. Okay. So looking at our diagram, we've got point P here is at 6a pi over 3, and the point Q here is at 6a minus pi over 3. It asks for the length PQ here. So there are a couple of different ways of doing it. You could work out this side length here and use a right angle triangle to work out this and double it, or you can work out this angle in here and use a cosine rule to work out PQ. Either way is fine. So this length here will be when theta equals 0, which will give me 3a. So, yeah. But we'll use cosine rule. So this angle in here, that's 2 pi over 3. So we've got our two sides of both 6a. So a squared equals b squared minus c squared minus 2b plus a. That's 6a squared plus 6a. That's 2 times 6a times 6a times cos of 2 pi over 3. 36a squared plus 36a squared is 72a squared minus 72a squared cos 2 pi over 3 minus a half. So 72 minus 72 times minus half, so plus 36. 108 squared. A was a poor choice for that one. This is PQ squared. So PQ is the square root of that, which I'm really hoping that root 108 is what I want. 6 root 3. 6 root 3. Okay, so find the point of intersection and then actually realizing that we've made a triangle, and you can just do. Depends a lot. Oh. Over the page, what we find in the area of. Okay. Okay, so now to find that shaded region. It looks so nice and so simple. It's not a semicircle, fortunately. It's a shape. I don't know. It's half of a card, yes. So to find this entire area in here, including R and this triangle, I'm going to integrate the curve C between minus pi over 3 and pi over 3. Okay, which will find that whole, it looks like a sector, but it's not. Then I want to find this area in here, this triangle, which I've got some lengths now. I've got the base of it. It asked me to prove that in there. We said this length here is 3a, so I could do half base times height to work out that triangle, and then I'll take them away from each. So first off, I'm going to integrate the curve. So I'm integrating between minus pi over 3 and pi over 3, or alternatively, actually, what I'm going to do is I'm going to integrate between 0 and pi over 3 and double it. That might be a bit easier because it's symmetrical. I can do that. And I'm integrating for a 1 plus cos theta squared. Okay, so you can do between pi over 3 and minus pi over 3. It's absolutely fine. I'm going to do just half of it and double it because I know it is symmetrical. So the 2.5 cancel out. Squaring this gives me 16a squared plus cos theta squared. You can pull the 16a squared out to the front because it's a constant. And I get 1 plus 2 cos theta plus cos squared theta. I'm going to use the double angle formula for cos. I'm using 2 cos squared theta minus 1 because I've got cos squared, which we've done last time. So I get cos squared theta equals a half cos 2 theta plus a half. So my integration is 16a squared in pi over 3 and 0. I'll have 1 plus this half from the double angle formula, so I'll get 3 over 2 plus 2 cos theta plus a half cos 2 theta d theta. Nice. Integrate this, 16a squared. Integrating 3 over 2 goes 3 over 2 theta. Integrating cos goes to sine. Integrating cos 2 theta goes to sine 2 theta, but got to divide by the 2. In pi over 3 and 0. Taking pi over 3. Sine pi over 3. So 2 pi over 3. And because I chose 0 as my lower limit rather than minus pi over 3, it's made my life a bit easier there. So I get pi over 2 from 3 over 2 times pi over 3. Sine pi over 3 is root 3 over 2. And by 2 root 3. Sine 2 pi over 3 is also root 3 over 2. Times by a quarter. Root 3 over 8. And then let's expand this out. So 16, so 8a squared pi. First term, here I will get 9 root 3 over 8 times by the 16 gives me 18 a squared root. Again, we haven't finished. Feels like children. We haven't. So I need to find the area of the triangle now. So I'm doing a half times the base times the height. Remember, the base is what we worked out in the first part of the question, 6.3a. The height is what I said, you stick in, I mean, theta is anything, but stick in theta equals 0 to get that height. Not theta, just get. And you get 3a. And if I work this out, so half times 6 is 3, that's 9 root 3 a squared. So the total area, I'm going to take those away from each other. 8a squared plus 18a squared plus 3 minus 9 root 3a squared. I wrote those the wrong way. So that gives me 8a squared pi plus 9a squared root 3. I've just got 18 minus 9. Very weird question. So cross section of a shell is modeled using this curve of polar equation r equals k theta. So this is a spiral out from the origin. You're getting further and further away. Here, where k is a positive constant. The horizontal diameter of the shell, it says there is 3 centimeters. So it wants us to find the value of k for that. Okay. So basically, what I want to find is these coordinates here, and I know the difference between them, or kind of the total length of each. Okay. So this is going between 0 and 4 pi because I started at the origin. We've gone up to here, which is pi over 2, down to here, which is pi, all the way around here, which is to 2 pi. So here is to 2 pi. And I've kept going around again. So up around here is to 3 pi. So this point over here is at 3 pi. And I've kept going all the way around here again, which is to 4 pi. So what I'm interested in for now is the coordinates of the curve at 3 pi and 4 pi. Okay. So when theta equals 3 pi, r equals 3 pi. Okay, so that's its length from the pole to that point there. That's 3 pi k. Okay, the r coordinate. But do the same for theta equals 4 pi. I get that r equals 4 pi k, which is this length in here. So the total length is 7 pi k. Total width. From adding those two together, that's equal to 3 centimeters. Okay, equals 3 over 7. That's not that much. Exact point. Okay. Everybody all right with watching? Very, very briefly, I want to find these two coordinates of this end point here, and then the total length will be equal to 3 centimeters. Yeah. So going around here, I've spiraled outwards. So I've gone to pi over here. I've gone to 2 pi here. Kept going around again. This one's at 3 pi. This one's at 4 pi. So I've subbed those in and got those radii, and then then it says, hence find the total shaded area of the cross section. So what I don't want to do is integrate between 0 and 4 pi, because you'll get some bits that overlap each other. Okay. So if you do the bit between 0 and 4 pi, you'll have some overlapping bits, like this bit between 0 and pi and overlaps this bit between 2 pi and 3 pi. So actually, if I split this up into 2 halves, this one's at 2 pi, this one's at 3, this one's at 4 pi. What I want to do is to find this top half here by integrating between 2 pi and 3 pi, and find this bottom part here by integrating between 3 pi and 4 pi. Okay, I think I should just be able to integrate between 2 pi and 4 pi. Okay, so I don't need to integrate between 0 and 4 pi. I'm actually going to integrate between 2 pi and 4 pi. Okay. So otherwise I'd get some extra overlapping bits. So the area is half of the integral between 2 pi and 4 pi of k theta. I'm going to leave it as k rather than putting that in. I'll put that value in at the end. Really easy integration compared to what we've been doing throughout this pack. So half k theta squared, 4 pi and 2 pi. Yes, thank you. Squared. I should be integrating k squared into squared. Thank you. But actually, it's a third k squared into cubed. In 4.2 pi. Sub that in. You could take the third k squared out, actually, if you want, which I will do. 6k squared. And I've got 4 cubed minus 2 pi cubed. 4 cubed is 64, 2 cubed is 8. That's 56 pi. So pi, let's put in our, simplify this and put in our value for k. So k was 3/7 pi. Squared. So let's deal with the numbers first. So 56/6 obviously will simplify, and I've got 3/7 squared. 12/7. Got pi squared on the bottom. I've got pi there, so I'll cancel with one of them. So I get 12/7. Yes, it's thank you. Yeah, thank you. The pi should be on top. I like how you waited until I finished it. Sorry.